Welcome to this presentation on the longest subarray with some K problem. In this session, we will explore the problem, the approach to solving it, and walk through its implementation. Let's dive in. The problem is simple. Given an array of integers and a value of k, we need to find the length of the longest subarray whose sum is exactly equal to k. For example, given the array with elements 10, 5, 2, 7, 1 and 9 and the value of k 15, the solution is a subarray of length 4. If no such subarray exists, we return 0. To solve this problem efficiently, we use a combination of prefix sum and a hash map. The prefix sum helps us track the cumulative sum of the array elements. The hash map will store the first occurrence of each prefix sum, allowing us to quickly check if we have encountered a sum that leads to a valid subarray. Key observations make the approach even more efficient. If the prefix sum equals k at any point, it means the subarray starts from the beginning of the array. If the difference between the current prefix sum and k exists in the hash map, we can calculate the length of the subarray between these indices. This gives us the longest subarray with sum k. Now let's break down the algorithm. We initialize the prefix sum as 0, the maximum length of the subarray as 0, and an empty hash map. As we traverse the array, we keep adding elements to the prefix sum. If we encounter a prefix sum that satisfies the condition we discussed, we update the length of the subarray. The algorithm works as follows. If the prefix sum equals k, we update the max length to the current index plus 1. If the difference between the current prefix sum and k exists in the hash map, we calculate the length of the subarray and update the max length. Finally, we store the prefix sum in the map if it's not already there. Let's now look at the implementation. In the first part of the code, we initialize the necessary variables, including the hash map and prefix sum. We also define a function that will take the array and k as inputs and return the length of the longest subarray. In the next part of the code, we iterate through the array, updating the prefix sum. If the prefix sum equals k, we update the max length. If we find a matching prefix sum in the hash map, we update the max length by calculating the length of the subarray from the earlier index to the current index. Finally, if we encounter a new prefix sum, we store its index in the hash map, so we can refer to it later if needed. This way, we ensure that we are efficiently calculating the longest subarray. Let's walk through an example to understand how the algorithm works. Given the array with elements 10, 5, 2, 7, 1 and 9 and the value of k as 15, we start by initializing the prefix sum and max length. As we traverse the array, we update the prefix sum and check for conditions. Continuing with the example, at index 3, we find that the difference between the prefix sum and k exists in the hash map, allowing us to calculate the length of the subarray. By the time we finish traversing the array, the longest subarray with sum k is of length 4. Now let's analyze the time and space complexity of the algorithm. The time complexity is big of n, where n is the size of the array, since we only traverse the array once. The space complexity is big of n because we store prefix sums in the hash map. The algorithm is efficient with linear time complexity and works with both positive and negative integers. It can be used in solving other subarray related problems, financial data analysis, and can be adapted for various use cases that require finding subarrays with specific conditions. In summary, the longest subarray with some k problem can be efficiently solved using the prefix sum technique combined with a hash map. The time complexity is big of n and space complexity is big of n. This approach is not only fast but also versatile in handling a wide range of problems. That concludes the presentation. If you have any questions or need further clarifications, feel free to ask, and thank you very much for your attention.